Hi viewers, welcome back to my class on mechanics of materials. In today's class, I will discuss two more numerical examples on thick cylinder. Let us start. A cylindrical pressure vessel has inner and outer radii of 200 mm and 250 mm respectively. The material of the cylinder has an allowable normal stress of 75 MN per meter square. Determine the maximum internal pressure that can be applied and draw a sketch of radial pressure and circumferential stress distribution. So here directly inside radius and outside radius are given. So you know Ri and R0, and allowable normal stress is given as 75 MN per meter square. So allowable stress is 75 MN per meter square. Meganewton per meter square means megapascal. Newton per meter square is pascal. So megapascal, 75 megapascal, which is equal to 75 Newton per mm square. And here this allowable stress means a maximum stress that can be permitted inside the cylinder or on the cylinder walls. So this happens on the inside surface of the cylinder. So we know that Hooke stress on the inner surface, that is 75 Newton per mm square. Now we are not given any other data, so we can assume outside pressure P0 as 0. We know that Hooke stress equation, Hooke stress is known inside corresponding to radius 200 mm inside radius. So you can write the Hooke stress equation. Hooke stress equation is sigma c is equal to b by r square plus a. So sigma c is 75, radius is 200 inside radius. So substituting the Hooke stress and radius corresponding to the inner walls, you will get one of the equation. Now outside pressure P0 is 0, and the equation for pressure is PR is equal to P by R square minus A. Pressure is 0 and radius outside is 250 mm. So 0 is equal to B by 250 square minus A. This will give another expression. Now here you have plus A, here you have minus A, because you have used Hooke stress and pressure equation. So now you can add these two, which will give 75 plus 0, 75 is equal to, here you have denominator 200 square, so b by 200 square plus b by 250 square. Now b you can take outside, b into 1 by 200 square plus 1 by 250 square is equal to 75. So you can solve for b, and we will get b as 1.829 into 10 raised to 6. So after getting b, you can either substitute in equation 1 or 2 to solve for a. So this equation will be easy because you have 0 on the left hand side, so you can substitute b as 1.829 into 10 raised to 6. So that divided by 250 square will give a. As taking that minus a to the left hand side, you will get a as b by 250 square, and solving that you will get a as 29.268. so this is another constant. Now you have to find out the maximum internal pressure the cylinder can be subjected to. So maximum internal pressure means on the inside radius, so you can substitute Ri inside radius 200. Okay, so substitute the Ri as 200 and in the pressure equation. So you know that b value and a value, pressure is p by r square minus a. B is substituted, a is substituted, and r is 200 corresponding inner radius. So we'll get the pressure as 16.46 Newton per mm square. So this is the maximum inside pressure possible to limit the maximum Hooke stress to 75 megapascal. So when inside pressure is 16.46 Newton per mm square, inner walls of the cylinder will be subjected to a stress of 75 megapascal or Hooke's stress of 75 megapascal. Alternately, you can use another equation, PR is equal to sigma c minus 2a, or sigma c, you know sigma c is PR plus 2a, or PR is equal to sigma c minus 2a. At any given radius, pressure and Hooke's stress are related by this relation, sigma c is PR plus 2a. Once you know the Hooke's stress there on the inner walls, Hooke's stress is limited to 75, and we solve for A. Now stress and constant A is known at a given radius. You can find out the pressure at that radius. So pressure is equal to sigma c minus 2a. Sigma c is 75 there, minus 2 into 29.268, which will give 16.46 Newton per mm square. So you can also use this equation. Okay. And to relate the sigma c and PR at any radius, you can always use this equation. If pressure is known, you can find out sigma c, and sigma c is known, pressure you can find out provided you know the value of A. Now to find out the stress on the outer walls, and that is Hooke's stress on the outer walls, you can use sigma is equal to B by R square plus A, and we know B and A. R is outer walls, it is 250 mm. Okay, you get sigma as 58.54 Newton per mm square. Or you can use the equation sigma is equal to PR plus 2A. If you find this easy, you can use this expression to calculate the minimum Hooke's stress. So PR is on the outer surface, we assumed that pressure is 0, and A we got as 29.268. So 2A, so sigma minimum will be equal to 2A, that is 58.54 Newton per mm square. So this is a plot showing the variation of Hooke's stress across the cylinder walls. So inside radius is 200 mm, outside radius is 250 mm. Inside Hooke's stress is represented here 75 megapascal, and it varies to 58.54 on the outer walls. So the variation is parabolic. You can show it by a curve. So only this you represent 75 and outside 58.54. So the variation is going to be parabolic, and you can show it by a curve. Now downward you can represent the pressure. Pressure is inside surface, pressure is 16.46, which you have calculated, 16.46 megapascal, and it varies to 0. Outside pressure is 0. So the variation is once again parabolic. So you can show that by a curve. So this is a representation of Hooke's stress and radial pressure on the cylinder walls. So the Hooke's stress is continuously decreasing with the radius. Radius increases, Hooke's stress is decreasing, even pressure is decreasing. Now at any given radius, say for an example inside radius, you know Hooke's stress. Hooke's stress minus 2A will give this. Okay. Similarly, Hooke's stress here minus 2A will give the pressure here. So if a pressure is known, pressure plus 2A will give the Hooke's stress. Or if you know that Hooke's stress and pressure at any radius, say for example outer radius, Hooke's stress and pressure is known, you can find out immediately A. Hooke's stress minus pressure is equal to 2A, so you can find out A. So here if you know Hooke's stress and pressure, Hooke's stress minus pressure, that will give 2A, and you can calculate the constant A. So in a given problem at any time, if Hooke's stress and radial pressure are given at any particular radius, you can take the difference and divide by 2, that will give the value of A. So you need not solve the equations to get A. Once you get A, you can use one of the Hooke's stress equation to find out the other constant B. Now let us work out another example. A cylindrical pressure vessel has inner and outer radii 150 mm and 190 mm respectively. If the internal pressure in the cylinder is 50 megapascal, determine the maximum and minimum value of circumferential stress on the cylinder. Also find the circumferential and longitudinal strain on the inner and outer surface of the cylinder. Given Young's modulus as 210 gigapascal and Poisson's ratio mu as 0.26. So you know the inside radius 150 mm and outside radius is also given 190 mm. So Ri and R0 is directly given. You know the internal pressure acting on the cylinder walls. So inside pressure Pi is 50 megapascal. Now you have to find out the maximum and minimum values of circumferential stress on the cylinder. So sigma max and sigma minimum you should find out. So you are not given any other data other than material properties which is required for calculation of strains. So you can assume the outside pressure as 0. So pressure inside is given 50 megapascal, pressure outside we are assuming as 0 or atmospheric pressure. So this is a gauge pressure. So atmospheric pressure can be taken as 0 gauge. So we know the pressure equation. So we know the pressure inside and outside. So we are going to use the pressure equation twice. So that will give two equations. So pressure equation is here is equal to B by R square minus A. Pressure inside is 50 megapascal corresponding to a radius of 150 mm. So 50 is equal to B by 150 square minus A. And also pressure is 0 when radius is 190 mm or outside radius. So pressure is 0 when R is equal to 190 mm. You get another equation, 0 is equal to B by 190 square minus A. So both the expression you have minus A. So we need to subtract equation 1 minus 2, that will give 50 minus 0 or 50 is equal to B by 150 square minus B by 190 square. Minus A, minus of minus A, that will cancel out. So you are getting 50 is equal to B by 150 square minus B by 190 square. Okay. Now B you can take outside. B into 1 by 150 square minus 1 by 190 square is equal to 50, and calculating B you get B as 2.986 into 10 raised to 6. Now substituting the value of B in any one of the equation, either equation 1 or 2, you get the value of A. Equation 1 or 2 you can substitute, but 2 will be more convenient because left hand side you have 0. So directly you can substitute B, and you can B by 190 square will be equal to A. So you will get the value of A as 82.72. Now inside hoop stress you can calculate as B by R square plus A, or here also you can use sigma C as PR plus 2A. That also you can use. Pressure inside pressure is known, it's 50, and A we have calculated. So 50 plus 2 times A will give directly the hoop stress, or you can use B by R square plus A hoop stress equation. So B and A are known. R is corresponding to inside we have 150 mm. So 150 square you can substitute. Substituting the radius 150, you will get sigma C as 215.44 megapascal. Or you use PR plus 2A. PR is 50 plus 2A, 2 into 82.72. That will give 215.44. Now corresponding to outside radius, you can once again use the hoop stress equation. B by 190 square plus A will give the hoop stress there. Here again we can use PR plus 2A. PR is 0 plus 2A, 2 times this 82.72, that is 165.44. So that value you can directly get by adding 2A to the pressure there. So pressure plus 2A will give the hoop stress. So corresponding to 190 you are getting the sigma c. So that will give the maximum hoop stress and minimum hoop stress acting on the cylinder walls. Inside you have 215.44 megapascal hoop stress and outer walls you have 165.44 megapascal. Now longitudinal stress in the cylinder walls you can calculate as sigma L is equal to Pi into Ri square. Since the external pressure is 0, that term will vanish. Pi Ri square divided by R0 square minus Ri square. Pressure, inside pressure is 50, Ri is inside radius 150, outside radius 190. Substituting that we will get the longitudinal stress as 82.72 megapascal. This will be half of the minimum hoop stress when there is no external pressure. Always longitudinal stress will be half of the external surface hoop stress. So minimum hoop stress is 165.44. Half of that will give the longitudinal stress in case no external pressure acting on the cylinder walls. External pressure acts, then this relation will not exist. Now you have to find out the circumferential strain and longitudinal strain on the cylinder walls. And since this is a thick cylinder, circumferential strain will vary from inner walls to outer walls, whereas longitudinal strain will remain constant. So to find out the circumferential strain, you have to use even the radial pressure, because thick cylinder will be subjected to large internal pressure. So that part also should be taken into the equation. So EC, circumferential strain, is given by sigma c by E minus nu sigma L by E plus nu PR by E. So this is a direct strain due to circumferential stress, this is lateral strain due to longitudinal stress, and this is lateral strain due to radial compressive pressure. The radial pressure which is compressive, so you have positive term here. So it is equal to 1 by E into sigma c minus nu sigma L plus nu PR. Now corresponding to inside surface, inside values you can substitute. On the inner walls you have sigma c, maximum hoop stress, and sigma L is always constant, so it's not changing with the radius, and PR inside pressure you have to substitute, that is 50. So sigma c inside value is 215.44, sigma L is constant 82.72, new value is 0.26 that we have substituted, and nu PR 0.26 into PR inside pressure is 50. So if you are substituting the hoop stress and pressure corresponding to the inner walls, you will get the circumferential strain on the inner walls as 9.854 into 10 raised to minus 4. Corresponding to outer walls, you have to substitute the hoop stress and pressure on the outside surface. So there you know the pressure is 0 on the outer surface, and inside surface we have calculated the hoop stress that you can substitute to get the circumferential strain on the outer walls. So EC on the outer surface is 1 by E 210 into 10 raised to 3. On the inner surface we have hoop stress 165.44 minus nu into sigma L. Sigma L is 82.72 longitudinal stress plus nu is 0.26 into outside pressure is 0. So that will give the circumferential strain on the outer surface as 6.854 into 10 raised to minus 4. So circumferential strain is decreasing. You can see that on the inner walls you have 9.854 into 10 raised to minus 4, and outer walls you have 6.854 into 10 raised to minus 4. So strain is decreasing. That means inner surface is subjected to maximum circumferential strain, and it changes from inner walls to outer walls. Longitudinal strain is given by sigma L by E minus nu sigma C by E plus nu PR by E, or 1 by E into sigma L minus nu sigma C plus nu PR. So this is going to be constant whether you substitute inside hoop stress and inside pressure or outside hoop stress and outside pressure, you will get the same value of EL. So let us find out the longitudinal strain. Longitudinal strain on the inner walls, substituting sigma L is 82.72 and sigma C on the inside surface you have 215.44 and inside pressure is 50, Poisson's ratio 0.26. Substituting that you will get EL as 1.8907 into 10 raised to minus 4. That is on the inside surface. And outside surface we need not find out the longitudinal strain, but for verification purpose you can check that outside surface corresponding longitudinal stress will remain constant, but hoop stress and pressure you have to change. So hoop stress is 165, hoop stress has decreased, even pressure has decreased. So but one term is minus, the other term is plus. So finally you are getting the longitudinal strain same as this value. So inside surface and outside surface you have longitudinal strain same. So that means same amount of stretching is taking place on the inner walls and outer walls in the longitudinal direction. That's all for today. Thank you for watching.